Metal spheres found in Australia have reopened a fascinating question: what exactly happens when human technology falls back through the atmosphere? The objects are small, strange, and easy to mistake for fragments of an ordinary machine. But their story leads into one of the most difficult problems in modern spaceflight: tracking everything we launch, everything we lose, and everything that eventually comes home. In this episode, we will follow the journey of a piece of space hardware from orbit to the ground. We will look at why reentry is so violent, how scientists identify unusual debris, and what these metal spheres can, and cannot, tell us about the future of space operations. The first clue is their appearance. Reports from Australia describe polished or partially melted metallic spheres recovered after a suspected atmospheric fall. Their surfaces are not perfectly smooth anymore. Some show darkened patches, heat damage, or shapes that appear manufactured rather than geological. That distinction matters. Earth is full of rounded stones, industrial waste, and strange metal scraps. A sphere alone is not proof of an extraterrestrial origin, and it is not even proof of a spacecraft origin. Researchers need a chain of evidence: where the object was found, when it appeared, what it is made of, and whether its chemistry matches known materials. The timing of a fall can provide a powerful first filter. Space agencies and private companies publish launch trajectories, re-entry predictions, and notices for controlled or uncontrolled returns. If a bright fireball or a debris report lines up with a vehicle passing overhead, the possibility of a connection becomes much stronger. But orbital mechanics is not a simple map in the sky. A satellite can travel thousands of kilometers during the time it takes eyewitnesses to report a flash. Atmospheric density changes from hour to hour, and solar activity can expand the upper atmosphere, increasing drag and shortening an object's lifetime. When an object drops from orbit, gravity is only the beginning of the story. A spacecraft in low Earth orbit is moving at roughly 8 kilometers per second. At that speed, the atmosphere does not behave like a gentle cushion. It acts like a wall of gas that compresses violently in front of the vehicle. The air becomes extremely hot, and shock waves form around a falling object. The familiar glow of a meteor or spacecraft re-entry is caused by a combination of compressed, heated gas and ablation, material being stripped away, vaporized, and carried into the wake. This process is uneven. Thin panels may disappear in seconds. Fuel tanks and dense structural parts can survive much longer. Titanium, stainless steel, nickel alloys, and heat-resistant ceramics each respond differently as temperature rises and aerodynamic forces pull the object apart. A sphere can be surprisingly durable because its shape distributes pressure smoothly. That does not mean it is indestructible. It may rotate, tumble, crack, or flatten as the surrounding flow changes. A hollow tank can also collapse or burst, while a thick-walled component may remain recognizable after the rest of the vehicle is gone. The key scientific question is not simply, did this come from space? It is, what object could have produced this material, this shape, and this pattern of heating? Scientists compare elemental composition with engineering alloys and manufacturing residues. They may look for weld marks, machining lines, coatings, insulation traces, or microscopic textures created during fabrication. The inside of a fragment can be even more informative than the outside, because its chemistry may be protected from the highest temperatures of re-entry. In some cases, the answer is mundane but still important. A fragment may come from a rocket stage, a satellite tank, or a spacecraft component. Identifying it helps improve re-entry models and makes future investigations faster. It also shows how much hardware remains in orbit after a mission appears to be finished. That hidden population is known as orbital debris. It includes inactive satellites, spent rocket stages, bolts, lens covers, paint flakes, and pieces created by collisions or explosions. Most objects are too small to track reliably, yet even a tiny fragment can damage a working spacecraft at orbital velocity. The danger grows because collisions can create more collisions. A single impact can turn two large objects into thousands of fragments, each traveling through a crowded orbital environment. This feedback process is often called the Kessler syndrome, a warning that some orbits could become increasingly difficult to use. The Australian spheres are interesting in this broader context because they connect an invisible orbital problem to something people can hold in their hands. Reentry is usually seen as a streak of light. A recovered object turns that event into physical evidence. Still, recovered debris must be handled carefully. A piece of a rocket may contain residual propellant, pressurized gas, sharp edges, or toxic materials. Officials generally advise people not to touch suspected spacecraft debris, and to report its location to emergency services or the relevant space agency. There is another reason for caution: dramatic claims can spread faster than laboratory results. A mysterious object often becomes a story about aliens before investigators have completed basic tests. Scientific curiosity is valuable, but the strongest explanation is the one that survives measurements, not the one that sounds most surprising. So what makes a space origin hypothesis convincing? One strong signal is a chemical signature that is difficult to produce naturally but common in aerospace manufacturing. Another is a clear link to a documented launch or re-entry. Several independent clues together can transform a strange find into a well-supported identification. The challenge is that modern space hardware is becoming more common. Thousands of satellites have been launched in recent years, and large constellations are changing the appearance and behavior of low Earth orbit. More launches mean more useful services, but also more objects to monitor and eventually dispose of. Responsible spacecraft design now includes the end of a mission. Operators may move a satellite into a disposal orbit, guide it toward a controlled re-entry, or design it so that it burns up more completely. Engineers call this demisability, reducing the chance that dangerous fragments reach the ground. No design can guarantee total destruction. Dense components are difficult to eliminate without adding mass, cost, and complexity. The goal is to lower risk, predict where debris will fall, and make sure people on the ground have as much warning as possible. Tracking networks provide that warning. Ground-based radars and optical telescopes follow larger objects, while international systems combine observations to estimate their orbits. When uncertainty is high, predictions are expressed as corridors rather than a single exact point. This uncertainty is why re-entry headlines sometimes sound alarming and then end quietly. A spacecraft can be expected to fall within a broad region, but the actual event may occur over the ocean, disintegrate higher than expected, or leave only a few surviving fragments. The atmosphere is powerful, variable, and difficult to model perfectly. For the public, the safest lesson is simple: an unusual metallic object can be a valuable scientific clue, but it should be reported, photographed from a safe distance, and left undisturbed. Investigators can then preserve its location and condition before testing begins. For the space industry, the lesson is larger. Every launch creates a responsibility that extends beyond the moment of liftoff. A vehicle is not truly finished when its engines shut down. Its parts may remain in orbit for decades, or they may return in a few years as glowing debris and unexplained fragments. The spheres found in Australia therefore matter even if they turn out to be ordinary rocket hardware. They remind us that the boundary between space and Earth is not empty. It is an active environment where materials are transformed by speed, heat, chemistry, and time. And they offer a rare opportunity to study the final chapter of a space mission. By examining what survives, researchers can learn what failed, what endured, and how future spacecraft might be designed to disappear more safely. The next time a bright object crosses the night sky, remember that it may be more than a beautiful streak. It could be a message from the engineering history of orbit, a fragment of a machine, returning through fire, and revealing the hidden cost of our expanding presence above Earth. If you enjoyed this journey from orbit to the ground, subscribe to The Quiet Cosmos for more calm, evidence-based stories about the universe, space technology, and the mysteries that become clearer when we look closely.